sports fans, hey, I'm looking forward to Boston, Golden State. Boston won the first game, so it should be a very competitive series. All right, let's talk about math here. Now, this problem is very similar to one that was reported as a problem solved in the Russian Mathematical Olympiad in 1999. I don't know the problem number, and I'm not 100% sure that's where it even happened. And it was a general proof that I'm going to present, but I just wanted to do a concrete example of this. To me, it's kind of interesting. It seems obvious, but this is a way to construct these conditions here. I just picked 585 arbitrarily, and it's an odd number, which kind of plays into the way that this goes. And we can express 585 as the difference of two positive integers or natural numbers, where each of those natural numbers have the same number of distinct prime factors. Now, again, it seems like it's something that probably would happen in probably an infinite number of ways, but to me, it's kind of neat to actually construct the circumstance. And what plays into this is writing 585 in terms of its prime factors. Now, this takes a little bit of time, but 585 is equal to 3 squared times 5 times 13. That's its prime factorization. So at this point, 585 has 3 distinct prime factors. Again, it's only 3. The 2 here has nothing to do with whether the prime factors are distinct or not. There's 1, 2, 3 distinct prime factors, namely 3, 5, and 13. Now, the approach here is to actually take the smallest prime that is not a factor of 585. And that would be the smallest odd prime. So that would be 7, which is what I wrote down right here. Now, you can, one way to write that is you're looking for a prime that does not divide. I think you've all seen this notation here. This vertical bar means divide. All right, and then when you put a slash through it, it means it does not divide. So 7 does not divide 585. Okay. You could actually say 7's not a factor of 585, the same thing. Y'all, this reads 7. This slash here means to negate this operator of divides. It's not an operator, but it's a 7 cannot divide 585, or 7 cannot be a multiple of 585. And that's what adds another prime into the process. Now, again, right here, we write down a very obvious statement after we start with 7. 7 times 585 minus 6 times 585 is certainly 585. But look what happens here. And it's a lot easier to do everything in terms of the prime factorization. It's a concrete example of using the prime factorization in a very nice way. So you end up, see how the 7 ended up here? So everything's the same. It's the very same as this prime factorization, except the 7 pops into existence. So this guy now has 4 prime divisors, 3, 5, 7, and 13. Now, the benefit of subtracting 6 is that it's an even number, right? And so 2 is going to be present because of the fact that 6 is an even number. And so notice again here, we have 1, 2, 3, 4 prime divisors. They're different, but that meets the conditions of the problem again. 4 prime divisors here, 3, 5, 7, 13. 4 prime divisors on the second one in the difference, which would be 2, 3, 5, and 13. So we met the conditions of the problem, and we've satisfied what we set out to do is writing it. 585 is the difference of 2 numbers, namely 4095 and 3510, each of which have the same number of prime divisors. Not the same prime divisors, the same number of prime divisors, and that's a distinction, of course. So I thought that was pretty cool. I hope you guys enjoyed it, and I'm going to present the general proof probably tomorrow or the day after. Go Boston.